All right, let's run through page 2 of the study guide. We're going to start with the function g of x this time, and g of x is equal to 1/3 to the x. We're going to do the same process that we did for problem number 1, which was 3 to the x. So remember, each of these x values right here are the exponent to 1/3. So it's going to be 1/3 to the -2, 1/3 to the -1, 1/3 to the 0, 1/3 to the 1, and 1/3 squared. So for each one of these, again, I'm going to start at the bottom and work my way up to the top. 1/3 squared means 1/3 times 1/3, which would be 1/9. 1/3 to the first is 1/3. 1/3 to the 0 is 1. Remember, anything raised to the 0 power is 1. Now, the 2 with negative exponents, all right? This negative means I'm going to flip this fraction over, all right? So this is going to be, instead of being 1/3, you would write 3/1 to the first. Well, that would just be the number 3, all right? 3 divided by 1 is just 3. 3 to the first is 3. Okay. I can do the same thing with this top fraction, right? I'm going to take this negative, which means I'm going to flip this fraction over. So it's going to become 3/1, and the power now becomes positive. 3/1 is 3. 3 squared is 9. So now I can use this table of values to graph. So I'm going to do -2, +9, -1, +3, 0, 1. Now I got to start being careful. So I'm going to go 1, 1/3, 2, 1/9. So this is a perfect example of exponential. Wow, hold on a second. That is a horrible line. I was wobbling all over the place there. Let's try that again. And what I was saying, though, before I interrupted myself, was this is a perfect example of exponential decay. So decay, you're going to start and you're going to just decrease the entirety of your curve. All right. Now, as we move to the right here, we're going to keep getting closer and closer and closer to the x-axis. We're going to get smaller and smaller values. We won't ever actually touch the x-axis. All right. Now that we have our graph of g of x done, part B, make a table of values and graph the inverse of g of x. So remember, we're going to take this these ordered pairs here, -2, 9, -1, 3, and we're going to reverse them. So all of these x values are going to become the function values here, 0, 1, and 2, and then all of these g of x values will become the x values. So it's going to be 9, 3, 1, 1/3, and 1/9. All right. So let's go ahead and graph those points. So we've got 9, -2, 3, -1, 1, 0. Now these are going to be the tricky two. So we've got 1/3 +1 and 1/9 +2. All right. So it's a logarithmic function, right? That's the inverse of an exponential is a logarithmic. We're going to approach the positive y-axis here, and then we're going to curve down and away here to the right. But on this upper part here, we're just going to get closer and closer to the y-axis without touching it or going through it. Okay? All right. All right. Yeah, close. Okay, so there's our two graphs, and one thing I didn't do with this one, it's always a good idea when I remember to, is to label the two graphs. It doesn't say so in the directions, but it's especially important at some point if you have two graphs or two lines on the same coordinate plane, make sure that you label both so I know which one's which and you know which one's which. All right, so we've got exponential decay here and the logarithmic inverse of the exponential decay. So let's start filling in some characteristics. Now, a lot of these characteristics are going to be just the same as the first problem. So domain for the exponential, everything is possible, right? -∞ to infinity. The range for the exponential is going to be from 0 to infinity, but you can't actually include the 0, so we got to use the parentheses. Okay. I'm going to keep going down just the characteristics of the g of x function. So asymptote, your curve approaches the x-axis but doesn't touch it. The x-axis is better known as y equals 0. X-intercept, we just said we never touch the x-axis, so there's none. The y-intercept, you can either see it in the ordered pair in the table, so 0, 1, or pull it right off the graph. So that's going to be the point 0, 1 there. Interval of increase or decrease. Because this is exponential decay, this graph is decreasing the entirety of its domain. So we're going to say this is decrease. As soon as I learn how to spell wow, that's horrible. Hold on a second. Let's try that again with something approaching legibility. All right, decrease. It's approaching legibility. All right, and that's going to be from negative infinity to infinity. And the goofiest one is, of course, the end behavior. So end behavior is as x approaches infinity, g of x is doing something. And as x approaches negative infinity, g of x is doing something. Now, I'm going to do this by looking at the graph. So I'm going to pinch in, go up to the graph. Okay. So from the origin, if I look to the right, what is this curve doing? That's what I'm trying to figure out. Well, the curve is getting closer and closer to the x-axis, which means it is getting closer and closer to a function value of 0. So that means g of x is approaching 0 as x approaches infinity. And if we look at negative infinity, so let me slide back up to my curve here. As we look at negative infinity, I'm going to look from my origin to the left. So as I move to the left, this graph is increasing up to positive infinity. Okay, so slide on down here, finish out the end behavior with positive infinity. So that's all the key features. Let me pinch in so you can see them all. That's all the key features for the exponential function. Now, I don't even need to look at the picture to know the places for the logarithmic function because I can use what I already have. So reminder, this domain becomes this range. So that's going to be negative infinity to infinity. This range is going to become that domain, so 0 to infinity. Everything x and y is going to flip. So this asymptote that says y equals 0, you're going to replace the variable y with the variable x, so x equals 0. This intercept is going to flip the order, so it's going to become the point 1, 0, which means it's turned into a the x-intercept, so 1, 0 here, and then the y-intercept becomes the one that's a none. All right, there is no y-intercept for a logarithmic function. Now, interval of increase or decrease, this one I want to look at the actual graph just to make sure my brain is telling me the right thing. So if I look at this orange curve from left to right, this graph is dropping the entire way, so it's a decrease. So we're going to say this is an interval of decrease. Again, I apparently can't spell decrease, even though it's written on the page. Decrease over the domain, but again, the domain is now from 0 to infinity. And last but not least, these end behaviors, I'm going to flip the x value with the g of x value and the g of x value with the x value to create the inverse end behaviors. So as x approaches 0, now again, this graph is only on the right side. So as x approaches 0 from the right, the inverse function is approaching infinity. As x approaches infinity, wow, that's horrible, infinity, the inverse function is approaching negative infinity. All right. Now, 100%, you could look at the graph to do that, but I really appreciate the fact, and I'll go ahead and label these with a little bit of highlighter. So this domain dropped here. This range moved up here. Asymptotes, you're going to swap the letters, so it's kind of hard to do an arrow there. So those two parts are going to reverse, right? The x-intercept and the y-intercept. If your exponential function is increasing, your logarithmic function will also increase. If it's decreasing, it's a decreasing. And then end behavior, you're going to switch the x's and the function values. All right. So I'm going to go ahead and close this video here. That's the first 2 pages. Let me know if you have any questions or concerns. And on separate videos, I'll do the next